Okay. I believe that should do it. Make sure we get that set up here. Okay. Alright, I think we should be good. A little bit of a hiccup there, but nonetheless, this should begin with another live stream. So, welcome everyone once more to another live stream. We will be dealing with once more another packet, the 2017 one. This is actually the one that I've done in my time taking this class for AP Calculus. Again, as always, this will be going through all 6 problems of the free response section. The AP exam is only coming within the next few weeks, and so I'm sure a lot of students are very diligently studying. So again, this live stream is meant to be a resource for those students, as all of this will be recorded on our main YouTube channel with the complete recording of us going through all 6 of the problems here. Okay, so I think with that, we should be good enough to begin. Again, we go usually through 2 problems at a time before we start looking at the answers in which we'll correct. So I think something that we can do first is that usually what I do as well is that we can go through and list down all 6 questions on this packet here as something that we can keep in mind as we go through all this. Again, each question is out of 9 points, giving us a total of 54 points that we could score out of this entire packet. So, as we've done many times beforehand, is that there are going to be questions on both sides of this packet here, in which we'll record them down and put them onto our notebook so that all of our work and the questions can be seen side by side so that we can get through each problem with plenty of precision and accuracy. Of course, something to note is that every time we start start any one of these packets, is that the first 2 problems are calculator sections, and so we will be using our trusty TI-83 Plus graphing calculator for the first 2 problems, and then the last problems, the 3, 4, and 5, all the way to 6, are all going to be without calculators. Okay? So, again, we'll be showing what each of the steps will need as we go through every single problem. Again, any sort of comments through the chat on the chat off to the side is going to be greatly appreciated for anyone following along or have any other math related questions for us at this time. So I think with that, we can begin with our 2017 AP Calculus, the free response questions, right? Abbreviated FRQ, and we'll be going through each individual one. Good. So let's begin with our first problem, and we'll copy down what we have here is a table. So we have the h described in feet, and a of h as a function, right, in square feet, and some sort of area looks like. So let's put this through and record down all the data points. So 0, 2, 5, and 10 right there, and then 50.3, 14.4, 6.5, and 2.9 are going to be the data points on this first set of the table here. And so the question itself has the context that they're going to be written down here is that a tank has a height of 10 feet. Then it says the area of the horizontal cross section of the tank at height h. Feet is given by the function a, where a of h is in feet squared in terms of an area. Okay. Then also tells us that the function a is continuous and decreases as h increases. Okay. And they give all those values that we recorded down earlier right onto the table. All right. Then to begin here at part A, it then tells us to use a left Riemann sum. With the 3 subintervals. Okay, indicated by the data in the table to approximate the volume of the tank. All right, and then we also indicate units. All right, very good. So we got a lot going on here, but first, of course, let's measure out all of the important data points here. Is that first off, the problem states that we have a 10-foot tank here, right, with the height at h that increases, then the area actually of the tank, right, will then decrease as h increases, right? So it says, right, the function a is continuous and decreases as h increases. Not something to note. It seems like it's going to be a more of a cone-sided shape, but not 100% entirely in that sense. Okay, but to part A, then we still use a left Riemann sum with 3 subintervals, and we still need to indicate units on that matter. Okay, because we are using a left Riemann sum of 3 subintervals, that means that for each of the heights of the rectangles that we're going to calculate, we are using the left-hand points. So 50.3, 14.4, and 6.5 respectively. Okay. So because of that, the volume will then be, again, given that we're using a left Riemann sum, right, we're going to find the area of a rectangle, meaning that it's going to be base times height, right? And then we just add them up as we go across. Right. So with the volume, then in that case, we're going to take each of the heights, so 50.3, the first one, multiplied by the base, right? Because 50.3 is the height. The base then is going to be the distance between the first 2 points, 0 to 2, right? So we can usually do that very simply with a subtraction of 2 minus 0. Okay. Then we add that with the next according height, which is going to be 14.4. And then the next 2 heights will be next 2 bases here is going to be between 2 to 5, right? So we could do another simple subtraction, so 5 minus 2, and then adding that lastly with the 6.5 and then 10 minus 5. Okay, as such, like that. Okay, then we can throw everything in here by running this. We can run this through a calculator, given that there's some decimals you have to keep track of. So with that, our line of work is still going to be the same. If our camera can focus on the calculator. Hello? There's plenty of light for this camera to focus on. Okay. I think with that should be good. So with our calculator here, it's going to be plugging in everything that we already have. So it's 50.3 times the base of 2 for the first rectangle, then a height of 14.4 times a height of 3, and then lastly adding that with the 6.5 times a height of 5. So each of these rectangles do have different heights. Well, I keep saying heights, these are bases, but they have different bases at 2, 3, and 5. Again, as noted from our table that we've been looking at earlier. So 176.3 looks like, all right, 176.3 is going to be the result of our Riemann sum here. And then because they did ask us to indicate units, right, because we've been adding everything up here, right, it's because these are heights or the areas. Again, this is the A of H and this is the H, right? So that's feet squared as the area of the tank at a specific height, height being given already in feet. Because we're multiplying that, that means we have a total unit of feet cubed because we are dealing with the volume of a tank, right? So pretty straightforward there for that first part. So we should be very equipped to go to the next one. So they're asking us in part B that does the approximation in part A overestimate or underestimate the volume of the tank. Okay, and we need to give our explanation as well. All right, so are we overestimating or underestimating the volume of the tank that we're dealing with, right? Something to note, of course, is that we have the A of H function, and something that came exactly from the problem earlier, right, is that it is a decreasing function for for A of H, of which we already took the Riemann sum for. So because A of H is decreasing, we can take a quick look as to what that might look like for our graph here. So if we have A of H, something like a very simple decreasing function, again, just as a sketch of the idea that we have, right? If we were to start taking the Riemann sum of such a function like this, right? Given we have our data points stretched out like this, right? Because we're choosing the left-hand Riemann sums, right? Because we're going left Riemann on a decreasing function, meaning that we extend outwards the left-hand points of this function, meaning that our total rectangles that we are taking areas of, as you can see, are lying above the function, right? Again, left Riemann sum, because that we take the left-hand point, extend it out, and make the rectangle out of the base between the two data points that we are comparing. So, because the function A of H is decreasing and the left Riemann sum was taken, it will be an overestimate for the volume of the tank. Okay, so this will be our nice and reasoned explanation mathematically to show that because we are decreasing and this function is going downwards, that we take the left Riemann sum. So again, these are the points on the left-hand side as we extend it out to the right to make up each rectangle as we go down. It's going to be an overestimate of the function itself. All right. Then going to part C, it tells us that the area in square feet of the horizontal cross-section at height h is modeled by the function f given by f of h being equal to the fraction of 50.3 all divided by e to the 0.2h plus h on the outside of that exponent. Okay, and then it tells us that based on this model, find the volume of the tank, including its. Okay, so because we have ourselves another function right here, f of h being equal to that fraction right there, okay, and because this f of h is going to be the area in feet squared of the cross section across this tank. So imagining if instead we had ourselves again the cylindrical tank as such, right? Again, f of h is going to be that cross section going horizontally across it, right? As we increase the height going up and down this tank, right? So it's not perfectly rectangularly cylindrical in the sense that the cross-sectional faces going horizontally across the tank are going to be the same all the way throughout, right? So because of this, we then have the equation of that area going through. That's 50.3. I didn't show that properly. Okay, so if we want to find the volume from there, that must mean that, right, a volume of the air, right? So the volume coming from an area equation must mean that it's going to be the definite integral of f of h in accordance to the height, right? So for us, we're going to need to go ahead and take the notes, of course, is that if we're going to plug this into our calculator, is that we go from 0 to 10 on the height, right? Because it did say earlier that the whole tank has a total height of 10 feet. So with that, we're integrating across from 0 to 10, right? So 0 to 10 in the total heights as we add up all the areas going up from 0 to 10, as is what a definite integral does. So because of that, we plug that directly right into our calculators with the fraction of 50.3 e raised to 0.2 times h in the denominator plus h waiting there, dh. This exact function gets thrown right into the calculator, and we should be able to follow up with a total volume. All right, so because of that, we can go ahead and take a look here that it's going to be the function integral, the 50.3 divided by all of e raised to the 0.2 times h. Let's see, we can use the variable of h. Now, where is that on my calculator? Right here. All right, so 0.2 times h, a little bit cut off at the lines there. All right, okay. So with that, we can go ahead and follow up. Lastly, I think we're going to need to, so with that, that's still in the denominator, so we can add the h there. That's an m. What is happening? That's an h. There you go. All right, so all of that is going to be inside of the integral. Then we tell the calculator that this is for the variable of h. Now we set it through our limits from 0 to 10. And with that, we should be able to have the calculator churn those numbers for us, and it will pop out 101.32, looks like, 325 rounding properly. So 101.325 feet cubed. And we have Daniel coming in telling us that plane geometry live in work, and he thanks us for that. Yeah. Yes, if that's a comment on us doing plane geometry live for you, yes, that's indeed what's happening here, right? As we are integrating from a two-dimensional plane into the three-dimensional volume, as is the question that is being asked in this free response section of this exam. All right. So with that, that is going to be the actual total volume. And remember, there's that because we're going from the two dimensions of a simple area, right? Area, by taking its integral by one factor of the height, it will change it by adding another factor of the dimension into the third dimension of feet cubed as a volume of the tank. That was pretty straightforward, at least in the work sense, so that's pretty nice. Then we can follow up lastly with part D of this problem, is that's going to tell us that water is being pumped into the tank. Okay, then it tells us when the height of the water is 5 feet. The height is increasing at the rate of 0.26 feet per minute. Okay, so using the f of h equation from part C, okay, they want us to find the rate at which the volume of water is changing with respect to time. Okay, all right, so we got not too much space here, but I like to think that we can just do this. Yes, Nicholas saying that just plain math taking place here. Yes, indeed. I'd say this is pretty plain math for calculus, but many other people would not think so. But nonetheless here, I think we can get everything set up here within the small space. Maybe we have to extend it to the next page in the back. But let's see here. Let's take note of what's important here, right? So we said that at the water being at 5 feet of the height, right, we have the height increasing at a rate of 0.26 feet per minute. So something to note is that now we're adding the time element here. So the change in height in respect to time is going to be a specific value of 0.26 feet per minute. All right, that's something that's going to be useful to note here. Of course, because we can use the original f of h from part C, given that this was area, right, we can then find the volume of the actual tank itself, right? So because we're dealing with a cylindrical tank, I believe in this sense, yeah, that's going to be the case here, but I'm trying to think about this. It's not really going to be cylindrical because the volume in any case, though, they didn't tell us cylindrical specifically, but in any case, though, with volume being equal to the area of the cross-section multiplied by the height, right? In this case, because of our previous work, is that the f of h is going to be the area equation that they told us before, right? Or the horizontal cross-section at any specific height is f of h. So with that, if we wanted to find the volume changing in respect to time, that's going to be a derivative across this entire function here, right? So f of h times h, right? So this guy, all this needs to have its derivative taken in respect to t, right? So because of this, we're gonna have to do this implicitly, knowing, right, by our previous work that dh over dt is going to be a result of the derivative of h, as well as the fact that, again, we have to keep in mind of the overall part of this function that we're going to have to deal with in this case here. So we are going to need a little bit of extra room on the backside, so let's carry this over here for a second. And unfortunately, with the lack of room, we have to start over on this. But nonetheless, though, we take over the important information that f of h before from part C. Again, this is the area equation of the cross-section of the tank. So 0.2h on the exponent plus h down there. Okay, and of course, the dh over dt that they noted earlier is that it was the 0.26 feet per minute. And then, of course, we wanted to know the height at exactly 5 feet, for which they were looking for the change in volume in respect to time, right? That was our objective for this part here. All right, so with that, we still have a few more steps to go here because, given that the volume is going to be equal to the area, so f of h times h, right? What that looks like equation-wise, of course, is just going to be 50.3 now multiplied by h. We just keep that factor of h there on the numerator, and the denominator is going to be exactly the same, right? 2h plus h right there, okay? So with that, then, we have to go ahead and start dealing with this part here. So, because we are going to go and use the actual, we need to find the derivative in respect, because that's the volume. We need to go ahead and start putting in this in terms of the dv over dt like this. All right, we can go ahead and take this guy and start using the product rule to begin to put into this equation here. I'm trying to think about this though, because there's a little bit of a problem in the sense of the actual implicit differentiation, given what our calculators can handle here. Yeah, okay. Why don't we go ahead and run this through what we already know beforehand, because we're trying to see here that, because like we're, yeah, okay. I'm trying to see, because it doesn't seem like we should be able to do this by hand, but I think we might have to. Okay. So instead of product rule, we might have to run this through the quotient rule of this type of problem, because, right, we're dealing with a fraction on this entire part here. Okay, so with that, we then need to go ahead and start doing our quotient rule. So we take the denominator, make sure we take this derivative respect to time, and then we leave the numerator alone, and then we take the I'm misremembering the quotient already. Wow. Okay, that's a little bit unfortunate because it's the numerator and we take that guy's derivative, right? And then subtract it with the numerator left alone, and then the denominator with its derivative. And then we square everything in the denominator. Just like that. Okay. It's very easy because we normally implicit differentiation is not done on the calculator, but nonetheless though we'd have to see how this works out on our end. So because this, we just work through each bit of line of work here with quotient rules. We leave that alone. Then 50.3, so that's 50.3 multiplied by the dh over dt, right? So dh over dt from there, right, will become that the 0.26 that they stated beforehand at the very start, right? The derivative h will not go to 1, it will go to that 0.26 feet per minute. Okay. Then we subtract that with now the derivative in respect to time for the rest of this. So the 50.3h stays the same. Then by taking the derivative of this guy here, so e to the 0.2h plus h on the outside, means that we have to go ahead and take the 0.2 again using the exponential rule. So that's going to be 0.2 coming down from the exponent spot multiplied by the dh over dt from there. So 0.26, and then the exponent is left exactly the same, and then we left it with the plus h, so that's 0.26, and then all this now divided by this left there squared. Okay, so a little bit of complex work here, I would say, because we had to expand this out all on the quotient rule because of this, right? But nonetheless, though, that is going to be the scenario for us in how we are going to then take the. Actually, have I kind of lost it here a little bit? I believe I'm going down a completely wrong line of work here, because if we've already found the volume from 0 to 10, though, it's from 0 to 10. Wow. Okay. Yeah, this doesn't seem like a very nice line of work that they'd want us to do on this exam. Let me quickly think about this for just another second here, because we already found the total volume at the 10-minute mark for this guy. Then if you want to go ahead and, well, it's not like it really gave us an equation on that either. Then by doing that, it's just going to be well, in any case though, we'll go ahead and stick with this for now, because we can then include this into our calculator. Remember that h being equal to 5, because that's the height in which they wanted to see this entire section to be worked on. So let's just make sure we can do this all properly without any other hiccup, and we should be okay for this. All right, so starting out here is that we need to make sure that we're going to do all of this first section here. So it's going to be e raised to the 0.2 times 5 for the height. Okay, so all this still added with 5 from this first section right there. Okay, then we take all that, keep it multiplied by the 50.3 times the 0.26 for the dh over dt. Okay, then all of this needs to then be subtracted by, now starting here on the left side, on the right side that is, of this equation. So that's going to be 50.3 times the height of 5 times now all of this last remaining part on the numerator part of this equation. So that's going to be the 0. Yeah, it's still multiplied. Yeah, 0.2 times 0.26, and then multiplied by e raised to the 0.2 times the height of 5 So all of this then needs to be added with the 0.26 weighting there on that other side there. And then we close everything off. And then we divide it now by the entirety of e raised to the, now the denominator, right? So this is going to be inputted right in there directly. So it's e raised to the 0.2 times the height of 5 plus the height of 5 weighting there. And all of this. I did that twice. Let's make sure I do that one properly. So it's e raised to that. Yep. And then why don't we insert in that parentheses to make sure that we just square the denominator only. And we get a fat 0. What in the world is happening here? How does that work get us a 0? Wow, this is getting even more confusing the more I think about this. Right, so let's take a look. Let's take another moment here to realize what's happening on this. Yeah, okay. That's what it seems like to me when I look back at my previous line of work. So we're going to have to take one more step back here. So this looks like this line of work isn't going to work at all for us because I was overthinking it when I taken a look after what our calculator thankfully saved us from total destruction. Here is that going way back. Let's try one more time with the volume function being equal to, again, the f of h times h that we've done before, right? But our previous line of work, though, is that our volume, right, that we found in part, I think this is part C's work, right, was going to be by taking that definite integral from 0 to 10 of the f of h function in respect to h, right? Again, this is by adding up all the heights across the entirety of the function there, okay? But thankfully, though, because we already know that this to be the volume, right, of the entire tank, right, we can use good old fundamental theorem of calculus, something that we should refer to beforehand, because we wanted to take the change of the volume in respect to time when the height is only at 5 feet, right, as what the problem stated at the very beginning of this part. Okay, so because of that, that means is that we are looking to instead, right, if we were then to just take the derivative from going from 0 to 5 for the integral, right, and then take its derivative in respect to time. By doing that, right, we'll be left with just f of 5 inside of the function, right, plugging in 5 only, and then subtract and then multiplying it by the derivative in respect to time for the height. Okay, so I think this line of work is going to be a lot better for us in that sense, right? Because of that, we can go ahead and do it easy plug-in, right, using fundamental theorem instead of our crazy line of quotient rule that we had to do beforehand, which didn't make much sense to our calculator, right? This was indeed going to be the way that they were going to go about this. Yeah, using fundamental theorem, knowing that this already was the volume, right, of the volume of the tank, right? So by taking that derivative in respect to time, we simply just follow a little bit of chain rule with fundamental theorem, then giving us the total amount that we need. Okay, so with f being 5 there, we can then plug that in nicer into our calculator from our original function. So 50.3 multiplied by a height of 5, all divided by e raised to 0.2 times 5 there on the exponent spot, plus 5 waiting after there, and multiplied by the 0.26 feet per minute that the problem gave us at the start. So with that, that will be a lot easier of a problem to be done on our calculators here. So going from here, we can go and start with the 50.3 times 5, all this divided by e raised to the 0.2 times 5, and then plus 5 still all there in the denominator. Then multiply all this by 0.26, and we get a proper answer. So 8.472. So with an 8.472, again, because we're doing the derivative of the volume in respect to time, right? That's just going to be the volume feet cubed in respect to the time. So it's per minute in which the volume is changing. All right. So it might have been a bit confusing given that we went down a completely wrong rabbit hole for this problem. But just as a reminder, right, because our volume that we found before of the entire tank going from 0 to 10 feet in height that we've done already in part C of the problem, right? Remember, because f of h is going to be the area, right? The cross-sectional area, sorry. So let's do the cross-section area for the tank, right? Coming across in the cylinder, right? Our volume in part C already was just simply the definite integral of f of h in respect to h. So because of this, if they want to find the derivative of that volume from part C, all that means that by fundamental theorem, by taking the derivative of the integral, now instead of going for the full height of 10 feet that they were asking for, right? They asked instead for the change acting on the 5 feet mark for the total tank, is that we just switch the limits from 0 to 5 instead for the original function inside the integral. Then by that and a little bit of chain rule is that we end up with us just needing to plug in f of 5 into the function of f multiplied by the change in height in respect to time, which they gave to us earlier as the 0.26 feet per minute. So with that, we end up with our total answer of 8.472 feet cubed per minute. So a little bit of a few steps for us, took a little bit longer than expected, but is still done properly. So I think that's what matters more here. All right, so that concludes it for part A. Let's move on to I say part A, that's part D of problem number 1. So let's go over to part number 2 here, in which now the context here tells us that when a grocery store opens, it has 50 pounds of bananas on a display table. Okay. Then it tells us that customers remove bananas from the display at a rate modeled by. So now we have this original function f of t being equal to 10 plus 0.8 multiplied by t. Now all that multiplied by the sine of t to the third over 100. And this is for the time interval 0 to 12. Okay, then it tells us that where f of t is measured in pounds per hour. Okay, and t is the number of hours after the store has opened. Okay. Then it tells us here that after the store has opened for 3 hours, store employees add bananas to the display table at a rate modeled by this new equation here. So we have g of t being equal to 3 plus 2.4 multiplied by the natural log of t squared plus 2t, and this is for the time interval from 3 hours onwards to 12 where the store closes. All right, so we've got quite a bit going on there for this part of the problem, but still, let's go over to the last bit here. So it tells us that where g of t is measured in the same pounds per hour, right? And of course, t being the hours since the store opened. All right, so we can finally get to part A, where we have knowing in fact that we have these two different equations here. One where customers are removing bananas from a display, and then the employees are adding more back. So part A is asking how many pounds of bananas are removed from the display table during the first 2 hours that the store is open. All right. So with that, we can go ahead and take a look here, right? They want to see how many pounds are removed just during the first 2 hours, right? So because of the fact that the f of t, right, this is the rate of removal. That's what the problem told us, right? And this is going to be measured in pounds per hour, right? We're not looking for pounds per hour, we're looking for just total pounds that are taken away from the display stand. So because of this, this will then mean that we need to go ahead and take the definite integral going from 0 to 2 for the f of t in respect to time for that question to be answered, right? Because f of t is going to be rate removal by taking out the definite integral of f of t, that is just going to be the total amount of bananas that have been removed between 0 to 2, which of course is going to be the first 2 hours of the store being open. So because of that, we will tell our calculators to plug in for this equation here. So it's 10 plus 0.8 times t, and then all that multiplied by the sine of t to the third over 100 dt. Right? This definite integral will then be calculated by our calculators here for problem number 2, and we will get our result from there. So with our function integral, remember this is the way that we can do definite integrals by calculator, is that we can then plug this in. So it's 10 plus the 0.8 times the variable t on that sense right there. And this is still going to be multiplied by the sine of now t raised to the third power over 100. Okay, so all that closed off there. And so we're telling our calculator for the variable of t to take it between the limits of 0 to 2. And we close that off. And so with that, our calculator tells us that it's 20.051. Right, so it's going to be 20.051. And because we integrated a rate in respect to time, we take back that one factor of the time. So just left with just pounds that have been removed from the stand. Okay, very good. Then they're telling us next to find f prime of 7. Right? Then using correct units, explain the meaning of that f prime of 7 that we just found. All right, so we got 2 steps right here. First step, of course, is very simple, to find that derivative, right? Which just means that we have to do the n derivative on my calculator. Again, plug in exactly f of t, telling it that t is then going to be equal to 7. For us, that's going to be quite simple, right? Which is going to be the math 8 button for us. So that's the n derivative. That's going to take the derivative of a specific function, put in there with respect to a single point on this type of function. So we plug everything back in exactly the way it is. So 0.8 times the variable of t multiplied by sine of t raised to the third power divided by 100. Okay, so this entire function is put back exactly the way it is, now in the derivative style, meaning that we have to go tell it that for the variable of t, it's only going to be one number at 7. Okay. So with that, it does give us a negative number. It gives us negative 8.1, I guess if you round it properly, it'd be 120. Okay. Now, the issue though is that by taking the f prime of 7, right, again, this is going to be, right, basically the pounds per pounds per hour, if I can write properly. And then we are again taking another derivative in respect to time for this function, right? By taking another derivative from the rate already, this means that the units will then be pounds per hour squared, right? That's going to be the first part, but we need to explain what that means in that sense, right? So that we need to tell the people here that f prime of 7, right, shows the rate of change for the rate of bananas removed from the display at the t is equal to 7 hours, right? Which is going to be the 7th hour after the store has opened. Okay. So with that, we have ourselves both the explanation and what the actual amount's going to be, the 8.120 pounds per hour squared for this banana stand. All right, very nice. So with that, we can go over to part C. It's telling us that, is asking us, is the number of pounds of bananas on the display increasing or decreasing at the t is equal to 5 point. Okay. All right. So at time is equal to 5, of course, that's something to note, because if you're looking for the increase or decrease on the number of bananas on that display, that means, of course, at time is equal to 5, given what they started at the beginning of the problem, is that 5 sits right inside of that time frame where we can use the GFT function on top of the FFT, because GFT, of course, is going to be the amount that the store employees are adding bananas back onto the display so that more customers can grab them off, right? So because of this, we have parts that are adding into it while we have parts that are removing from it, okay? So given the fact that GFT is going to be the adding factor, and then by subtracting with FFT, right, because this is the rate of removal, right, this could then tell us, right, the total amount of bananas, right, increasing or decreasing based off the sign, right? Of course, if there is more removal than adding, of course, the amount of bananas on the display is going to decrease. Well, in another sense, if the employees are adding more to it, the total amount of bananas on that stand is going to increase. Okay, so because of this function, this little equation that we set up here with the GFT being subtracted by FFT, keeping in fact of the matter that there are employees adding bananas while customers are taking them off, is going to be the point of contention here. So with that, looks like we just need to plug in everything here, right? Given that it's going to be at t is equal to 5, that's g of 5 minus f of 5. So in our calculators here, we're going to plug everything in accordingly. So starting with g of 5, that's going to be entirety of 3 plus 2.4 times the natural log of 5 squared plus 2 times 5, with the t all plugged in there. And then with that, we subtract it from the f of t. So that's 10 plus 0.8 times a 5 times the sine of 5 to the third power over 100. A little bit shoved in there in our paper, but still, this is just going to be the line of work that it's going to be thrown into our calculators. And so with that, we can get our result here. Okay, so with the start here, so with the start of our plugging in here, that's going to be all of 3 plus the entirety of 2.4 times the natural log. Let me do that. Natural log of 5 squared plus 2 times 5. We just do that in our head, so that's really 10 waiting in there inside the natural log. So all that closed off there like that. And then we subtract it with the entirety of f of t, so it's 10 plus the 0.8 times 5. And all of this is still multiplied by the sine of 5 raised to the third power divided by 100. We close off the sine, close off the subtraction, and with that we get the total amount of negative 2.263. Okay, so it's negative 2.263, and the unit's still going to be pounds per hour, right? So because it is a negative number, let's make sure we can show all of that, right? So negative 2.263. So again, this is going to be the bananas on display are decreasing at the time is equal to 5 hours, because we have a negative sign as a result of our work here, right? And because of that, again, the amount that the customers are moving are going to be more than how much the employees are adding into it. All right, so we have part D to go over, so we are out of space here already. That's kind of a symbol of us doing good math work, but nonetheless though, we must flip this over to get over to part D so we can finish off problem number 2, which is going to ask us how many pounds of bananas are on display at the t is equal to 8 mark. Okay, so if you want to see the total amount of pounds of bananas, of course, because, right, again, f of t is going to be rate of removal, and that g of t is also the rate of adding back to the stand, right? Because these are both rates, if we want to find just the total pounds of bananas that are going to be on that display, we are going to need to go ahead and take an integral, right, of this respect to time for this. Okay, and because we're taking the integral and at this point in time, given the fact that we're looking for a specific time in which this is happening, right, we have something to keep track of. So again, a lot of little rules here which they've already been explained in the problem that we just need to keep track of if we are looking to answer this one properly. Of course, the fact, of course, that g of t doesn't start, right? The g of t function, according to the problem, does not start until the time is equal to 3, right? Because this happens at the 3rd hour, right? The employees don't start adding bananas back immediately. They wait until the 3rd hour in which they start putting them back, right? And of course, we still have fundamental theorem to contend with. Right? What does that mean? Of course, is that because this doesn't happen until the 3rd hour, we have just the first integral from 0 to 3 hours, right? For this first definite integral to take place. But then on top of that, then we start with our second integral, then going from 3 all the way to the 8th hour. Right? This is going to be f of t minus g of t dt like this. Yeah. So this is how we get this started off. But on top of that, right, we have a couple of things to note, right? Given that we're using fundamental theorem of calculus, what this is telling us, right, is that first we're just doing a simple subtraction question here, right? Because we're going back by doing the, right, this is going to be the capital F of 3 minus capital F of 0, right? This is going to be the change in the amount of bananas that took place, right? Knowing that F of 0 from the start of the problem was a 50 pounds starting, right? That's how many pounds of bananas that we started with. Well, then we do that subtraction. That means this is going to be left with how much bananas were taken away during that entire time. All right. So because of that, right, then on the other side of things, right, on this other side, we're going to do the hang on. This is actually not going to be correct because it shouldn't be f minus g. It should be the other way around. It should be instead the g minus f. Right. So in this case, right, by doing the change between 3 to 0, right, given that the starting amount was at 50 pounds, right, this is going to be the first integral is then going to be the amount removed from the 0 to 3 hours, right? And then we need to add that with, of course, the amount removed from 3 to 8 hours. Okay, all of this, of course, needs to be in comparison, right? Because all these are going to be the amounts removed from both integrals, from 0 to 3 to from 3 to 8. If we were looking to see how many bananas, right? So let's use a function b, right? So bananas at 8 hours means that we take our original 50, right? The 50 pounds starting. Then we subtract that with the 0 to 3 integral of f of t dt. And then we then subtract that lastly with going the other way now. So 3 to 8. I'm trying to do actually, no, if we're going the other way, then that's going to be addition. So g of t minus f of t. So because of that, yeah, if there's any negatives as a result, then they'll be subtracted away from this amount. So this is how we're going to set this up into our calculators. And this will take a few lines of work, but we should be all the better for it from that. Okay, so let's see if we can put this all in our calculators to find out exactly how many bananas there are at the 8th hour here. Starting it out, we have 50 bananas to start with, but then we need to go ahead and subtract that now because we know that bananas are going to be taken off from the stand, but the amount is just going to be the difference between the 0 and 3 hour mark. So because of that, this is going to be 10 plus all of 0.8 times t times the sine of t to the third power divided by 100. So all this will be going from the variable of t going from 0 to 3 for this one. And then we add that with now the integral of, this is going to be the g minus f, so it's going to be entirety of 3 plus 2.3 plus, let's make sure we do this right, so all the entirety 2.4 times the natural log of t to the second power plus 2t right there. Okay, so all of this, yep, will then be, well, not that just yet, so we close it off there. Yeah, one more, and then we subtract it from f, so we put that back in, so it's 10 plus 0.8 times t right there. Okay, and then multiplied by the sine of t to the third power divided by 100. Okay, so we close all of that finally off. Then for the variable of t, now from 3 to 8 hours there. Okay, and they're just gonna yell at us most likely because we forgot one of the parentheses. I think if we took out a parentheses, we should be fine. Yeah, I think I did too many parentheses. There we go. Okay. So we end up with 23.347 bananas. That seems to at least make enough sense for us. Again, the customers are removing a lot of bananas there. So 20.347 pounds left. Okay, so this was just a test to see how many things we can account for. Again, according to the fact that G does not take into consideration until the third hour and onwards, right? So we have to keep in fact of how many were removed during the first 3 hours, and then we continue removing from the third to 8th hour while we keep in mind for the employees adding them back. All right, so that will about do it for the first two problems. So let's actually go ahead and see, after all of our hard work here, how well we've scored so far. Okay, so let's go back to the first problem here, and we can swap the screen over to our first section here. So we can put this side by side here with what we have here on the first problem, right? And our actual answers to this. Okay, so problem number one, again, they were asking for the using the left Riemann sum to then find the volume of that water tanker that we were first solving for on problem number one, right? So because of the left Riemann sum, we have to do, again, each of the heights on the left-hand side multiplied by each of the bases by taking the difference of the x values. So because they want us to show that we are doing the left Riemann sum properly, that's exactly how we're going to set it up, with an addition of all the areas multiplied out and then added up together. So that's going to be the first point right there. And then 176.3 cubic feet is indeed going to be the correct way to show this. Okay, so that's the first 2 out of 2 already correct for this first part right here. Okay, and then going onwards to part B, they're asking to see if this is going to be an over approximation or an under estimate for this type of function. So again, given the sketch was here just to show us visually a little bit what that works, but because they're looking for the answers in words here, is that it is indeed going to be an overestimate, right? Because the function is decreasing and we're using a left Riemann sum, right? So them us showing the overestimate, and the reason, of course, is going to give us just 1 out of 1 correct on part B. Then going to part C, they want us to find the total volume using this equation f of h of the area equation at any given height. So because we are given an area, by taking its integral respect to height, going from 0 to 10, plugging all that in there, right? Setting up the integral properly, and then the answer of 101.325 feet cubed, that's exactly going to be correct. That's another 2 out of 2 correct to show us for that. Okay. Then lastly, on part D, this took a little bit of time for us, but nonetheless though, they gave us that by using the volume back in part 3, they want us to find the change in height in respect to time. Instead, right, that's what they gave us, the change in height in respect to time. They want us to look for the change in volume in respect to time based off of what we were doing beforehand. Right, we have to flip the page over to see the rest of the work. Again, it's going to start down here. We went down a little rabbit hole, which wasted a bit of time, but nonetheless though, by us finally understanding that fundamental theorem is going to be used, by instead right, by taking the derivative of that volume that we've found beforehand, right? The volume being the integral of the area function f of h, right? So by taking the volume, taking the derivative of that and reverting back to the area multiplied by the change in height in respect to time at the 5 meter mark, 5 foot, yeah, the 5 feet mark for the height, right? We just have to simply do a plug-in, multiply by that coefficient of 0.26 feet per minute, and with an area multiplied by a rate in height, we finally do get the, well, this is actually not very good for us. They actually get a different answer here. 1.69, okay. So let's go ahead and take another look at this, because everything else seems to make sense. Our setup is actually 100% correct. The f of 5 times dh over dt. I wonder if one of my parentheses off can actually be in this case here. So let me quickly go ahead and plug this back in here. The 50.3 times 5 for this, and then divide it by the entirety of e raised to the 0.2 times 5, and then plus 5 in that denominator times 0.26. Huh. That's a little bit odd. That still seems to be the, let me double check the original equation now. Something does not seem to be right with what we're doing. Huh. Let's see here. It's still giving us an 8. 50.3. Oh dear. Yeah. That times 5 should not have been there. That was from a previous wrong line of work there. So if we did not have that, 5 back there, if we got rid of that, so we left it at the 50.3 by itself. I unfortunately copied things down wrong. Indeed, it'll be 1.694. So 1.694, again, this 5 coefficient should not have been there. That's a problem, my fault. On that, this is actually going to be the correct answer. So because of that one silly mistake of carrying over a 5 when it should not have been, after all of our hard work here, sadly, because the setup is correct, actually, because us understanding how to take the velocity in respect to time, and the setup was exactly the way that they wanted it to, just that our work and the calculator wasn't correct. This is just going to be 2 out of 3 correct for this part instead. Okay, so unfortunately, by missing this by 1, we only get a total amount. Instead, on our record here, I have 8 out of 9. Okay. A different student does ask us that they're looking to for some help on AP Chemistry. Yes. You might have seen this. Unfortunately, I don't have this set up here, but there is... let me see if I can type this in, actually, really quickly here. Actually, we can set this back before we move on. So I'm going to go over to question number 2, but again, it's there over on the left-hand side over there, the labcoatmath@gmail.com. I can put that into the chat here on this side as well. So again, our viewer LQBD9, again, any questions can be directly sent to the email labcoatmath@gmail.com. Again, AP Chemistry is good too. Okay, there you go. So hopefully that will be a good enough link to send that through. Yeah, we've had a couple email questions being answered on the history of our channel so far. But yes, actually, now that you note that, AP Calculus AP Chemistry will be the next subject to be discussed in once the AP test is actually over, for a bit of a summer session that we can definitely go over. We are looking to hopefully expand into other routes of education as well, with chemistry being one of them. Okay, but again, any other direct questions you can send directly through the email if you are looking to get any of them answered in the meantime. Nonetheless, though, let's go ahead and get back to our second part of this problem here. So we're going to go downwards to question number 2 and grade that before we continue forth. So again, this is the whole bananas in the grocery stand. So with that, we can go ahead and start taking a look here to see how this will measure up. Okay, so part A, again, they were asking for the amount of pounds of bananas removed just in the first 2 hours, right? So as seen there on, actually, I remember I was doing this last time. Make sure we can keep that in mind. No, we do something like this. So that way, there you go. Now we can see a lot of great annotations. So again, they want us to see that we set up the equation properly like that. Okay, with the FFT of dt going from 0 to 2 hours for this first part. Okay, so with that, right, we set that up exactly the same way too, right, with our going from 0 to 2 FFT dt, sent right there. And so because of that, we just had to plug that in directly straight through as the amount of bananas removed on the first 2 hours. So this ends up with 20.051 pounds, exactly the way that they want this to be done. So with both the integral and the answer done correctly, that's 2 out of 2 correct on this part. Okay, then going on to part B, they were asking to see how we can get f prime of 7, ending up at the negative 8.120. I wonder if I should actually lower that opacity a little bit more there. Something like that. There you go. I think that shows up a bit better. Okay, so instead of with the f prime of 7, ending up at the negative 8.120 pounds per hour squared. Again, this was done properly as well. All right, we're just taking a simple derivative at a specific point. Then, because we have the rate of change sent right there, straight through the problem, right? Again, this is going to be, again, the rate at which, right, the banana is being moved, again, they say is decreasing, and the pounds per hour, right? Again, that is going to be the correct forms of units. Per hour squared is just a way to clean that up a little nicely. But yes, that is how the rate of change is being changed again, right? Out for which at the specific time at 7 hours after the store has opened. Okay, so because the value and our explanation are both good, in this case, that will be 2 out of 2 correct for us on part B. All right, then lastly, moving down onwards to part C here, it's going to be asking us, right, to see if the number of bananas are increasing or decreasing at the time is equal to 5 mark, right? So because we're looking for simple increase or decrease, they were indeed just looking to see the difference between G and F at the time is equal to 5 mark that we have shown exactly in the same way right there as the answer key. Then running it down gives us the final answer of negative 2.263 and shown properly right there. So that's going to be the correct answer right there. And of course, the reasoning is that it indeed is going to be decreasing because we have a negative there as the sign of this, right? Meaning that F was larger than G, meaning that they are being removed faster than the employees are putting bananas back on the stand. So because of this, this will indeed give us once more 2 out of 2 correct for part C. Then let's go and conclude back downwards to part D, which we did have to do on a separate, on the next page over. But nonetheless though, we still had all this to keep in track of, right? Because we were going to go and do, they actually made this look a lot nicer than I could have. They actually, the work is still going to be exactly the same. They just split this up a bit nicer instead, with their line of work being 50. Then we're going to add from 3 to 8 hours for the total amount of bananas added, subtracted by 0 to 8 FFT dt. Right. Again, by this meaning, of course, that this is going to be the total bananas added. Again, remembering that we start at the 3 hour mark. Well, from 0 to 8, this is all the time that the bananas removed. Okay. All right. So again, nonetheless, though, this all still works out the same way, just a little bit of an easier time of the way of putting this through. But still, it's going to be 2 integrals, of course, because one's for G and one's for F. But nonetheless, though, the answer still matches up exactly the way it should at 23.347 pounds of bananas left. Right? Again, there's just a different way of making the work look or appear separately. But nonetheless, though, integrating properly and, of course, getting the right answer will give us all 3 out of 3 correct in both the setup and the final answer that we've gotten there. So thankfully, we've redeemed ourselves a little bit here on part question number 2. So with that, that's going to be all that correct. So that's 9 out of 9 entirely for question number 2. All right. Very good. So we can revert back because we are going to continue forth with our exam here. Again, practicing through all of the questions on this part here. So because of this, again, the email is right. I should make sure on the next time I can add that email link down there even while we're grading, so that any of the viewers that might have other questions can definitely send emails directly to our labcoatmath@gmail.com email, so that any other live questions can be answered on the live stream or later on in a separate video. Nonetheless, though, because we're continuing forth with question number 3 as shown on the packet, again, the no calculator section for questions 3 through 6. So with that, we will very diligently put away our very trusty graphing calculator and leave it off to the side as we move on with this exam. Okay, so going on to question number 3 here. Okay, we are going to, looks like, copy down this graph here. That we'll be needing to, looks like, refer back to during this time. So with this, we can go across 6, 3, 4, 5, and 6 right there. We go up by 3. Then we go across, looks like 4. Okay, we just need to go down 2. Okay, so we go from -6, comma, +2 up there. Right? So that's -6 back there. Then we hit the axis at 0 right there, at -2. Then going down, we go down to 0, comma, -2 down there. And then we go back up at +2. Then at 3, we go up to +2. And then we go back down. Okay, so we've straight line down there. Then we have, looks like, a semicircle right there. We go up and down like that. This is going to be, as a note, this is graph of f prime. Okay, very important little detail right there. And let's get to the context on this. So it tells us here that the function f is differentiable on the closed interval going from -6 to +5, okay, and satisfies, let's see, the point f of -2 being equal to +7. Okay, and again, the graph of f prime consists of a semicircle and 3 lines. Okay, and that's shown exactly right there. We do have a semicircle coming across from -2 to +2, and they confirm that in the wording of this problem. All right, let's get on to part A here. It tells us that they want us to find the values of f of -6 and f of +5. Okay, very good. So with that, we have our values listed out right there that they want us to find. And because they want to find original f, remember this is the graph of f prime and not the graph of f, we're going to need to do a little bit of integration to run the step backwards from the f prime down to the original f functions. But of course, because we need to use fundamental theorem of calculus, and we have the original point of f of -2 being equal to +7, we can use that to advantage, knowing that we can then take the definite integral from -6 to -2 of f prime of x, right? And that will give us the difference between 2 points of f of -2 subtracted by f of -6. With that, of course, because we are looking to isolate f of -6 instead of f of -2, because that's already given to us, we just have to move things around. And we get f of -6 then being equal to f of -2 now subtracted by the definite integral from -6 to -2 of f prime of x dx. And because of that, right, f of -2 is already 7, and from -6 to -2, that's just going to be the area underneath that graph of f prime. Okay, so because of that, we can go and start working on this, right? Going from -6 all the way to -2 is just going to be a nice triangle for us, as you can see, right? Going as the area underneath the entirety of this section of the graph. Okay, so because it's a triangle, that just means that we can set this up as an area of a triangle equation of 1/2 times the base. Going from -6 to -2 means that it's going to have a base of 4, and the height, with it being already listed out here again, that's at the height of 2, right? So 1/2 times 4 times 2, again being with the 7 subtracted by all of that, So with a bit of work here, 1/2 will cancel with that coefficient of 2. So this is going to be 7 minus 4, meaning that f of -6 is equal to +3. Okay, that's our first answer already. Within the next first two, because next they want to know f of 5, so still using fundamental theorem of calculus, we can go instead from -2 to +5, ordering this properly. Again, going from the smaller number to the larger one. By taking the derivative of f prime of x, we can then go and realize that they're asking for the difference of the points of f of 5 minus f of -2. Then by isolating f of 5, that's going to be instead the f of -2 being added to the definite integral from -2 to +5 f prime of x dx. Okay. A little bit of movement there. Again, we can still note that f of -2 is a +7. But going now from -2 all the way to +5, okay, which I kind of wrote that wrong, right? The line there is at 5. That line there doesn't exist. But nonetheless, though, I think I can use a different color to really simplify this out. That we have to find the area underneath that triangle there again. We have another triangle to deal with. And of course, we have all this area now to contend with that semicircle there down at the bottom side there. Okay? So because of that, we have two things here, right? We have the area of a semicircle. And of course, I note that this is going to be negative, right? As it is indeed underneath the x-axis for the total area. And then we need to add that with the area of the triangle. Okay, so now this semicircle, of course, will have a radius of 2 going from the center from 0 to 2 and all sides, right? Semicircles, of course, meaning that a coefficient of pi over 2 is going to be needed because we're cutting this circle directly in half. And again, now it's just r squared, so the radius being 2 being squared. And then adding that with our triangle, so still it's 1/2. The base now going from 2 to 5 means that it's going to have a base of 3, and then a height still of 2 going all the way up. Okay. We can cancel that out. One factor of the 2 will cancel out there. So, and because we need to keep track that it is a negative because the circle, again, is underneath the x-axis there. So with that, this is going to be all +3 minus a 2 pi as a result of that area. Okay. So along with that, we can go and finalize everything here. So this is going to be f of 5 being equal to 7 plus 3 minus 2 pi, giving us a total of 10 minus 2 pi, combining like terms. And that's going to be f of 5, the other point that they're looking for on this problem. Okay, so what that looks like, we got all these 2 points already settled out right there. And so then they're going to ask us next that on what intervals is f increasing? Okay. And we need to justify our work along that line. Okay, so if they're looking for f being increasing, of course, all that just means that the first derivative of f needs to be greater than 0. Thankfully, it is on the graph. We already graphed out all of f prime that they want us to see, right? So because all we need to know if the original function f is increasing, that just means that the derivative must then be greater than 0. That just means we need to find all the points in which we're going to be above the x-axis. Okay? So because of that, that just means that for, right, so that means f is increasing on, now we have the intervals again now going from -6 all the way to -2. Again, the start of that semicircle at -2. So -6 going to -2. And we have that second part now going from +2, again being above the x-axis, all the way up to +5. And those two intervals will be the case in which we are indeed increasing on that function. Very straightforward. Okay. So because of this, then we want to then find on part C the absolute minimum value of f on the closed interval -6 to +5, and we need to show our work for that. Okay. Absolute minimum, of course, means that, again, as we've done many times before, this is going to be a look to see at the candidates, right, that are going to be possible, and we must compare all of them, right? That must mean that we're looking at the endpoints, and a local minimum. Okay. Endpoints are quite nice because, of course, if we're going to make a table of these values, okay, means that the x values and the minimums are just going to be at the endpoints as -6 and +5. Again, the starting and ending points, because those could be at any time the highest or lowest points of this function. But then, of course, a local minimum must go back to looking at the times in which the first derivative is equal to 0 and doing a number line approximation, number line analysis, that is, to make sure that we are local minimums on that matter, right? So we are first going to look at f prime being equal to 0, which on the graph looks like there's only 2 points at -2 and +2, where again we touch 0 on the x-axis, or touch 0 on the y value for the graph of f prime. So because of that, we will take those 2 points and we'll take a look. So at -2 and +2, we are touching 0, but then that also means that we need to go and take a look to see what that means for us when we go and start looking at the way those signs change, right? So again, being a minimum means that we must transition from a negative to a positive on that first derivative, meaning that we are decreasing, right? Our function is going down, and then it follows by going back up again, right? That's going to be a local minimum in our case, mathematically, meaning that the first derivative must go from a negative to a positive after crossing a 0 on the x-axis. Right. So because of this, as you can see from -2, our first point that we're looking at, we're going from positive numbers all above the x-axis, then below, right? So going from positive then to negative, that means it's going to be a local maximum, not a minimum, so that's not good for us. But going onwards to +2, as you can see here, we're going from the negative side, we cross 2, and we go back to the positive side afterwards, right? So because of this, this is mathematically going to be a local minimum for the value of 2 on this function. So because of that, 2 is going to be our third candidate, and then we must take a look at all of them. Thankfully, though, we've already found f of -6 and f of 5 on our first problem here, right? With f of -6 being +3 and f of 5 being 10 minus 2 pi, right? So we can keep those off to the side. Thankfully, we've already done that already on part A, which is very nice. Okay. Then we have some encouragement from the viewer Salman telling us that we're doing a great job. Yes, thank you for coming in and telling us that. Indeed, yeah, we're trying to do the best that we can. I think we're trying to hit a record as to see what grade of a score we can get here. But nonetheless, though, we're still trying to finish part C here, what we're going to do on this calculus exam, to try to see if we can find that absolute minimum on this part of this question here. So with x being 2, right, we're looking to see what we can get on f of +2. And because of that, we still need to go back to using fundamental theorem of calculus that we've been doing this entire time on our previous lines of work on part A, meaning that we can set the definite integral going from -2 to +2 on the first derivative graph, meaning that, right, by using fundamental theorem of taking the integral of a derivative, we will then go back to taking the difference of f of +2 minus f of -2. Okay. So because of this, right, f of +2 is then going to be equal to that, putting that -2 onto the other side, then adding that with the definite integral of f prime of x dx, right? So because of that, we can then, right, from what was stated earlier in the problem, that f of -2 is equal to 7, that's something that they gave us there as a point to start out with. So we get +7 there, adding with this definite integral. And because it is a definite integral, it's going to be area underneath the f prime of x graph, which was already graphed out here, which again is going to be that semicircle going from -2 to +2. And the semicircle we found already a bit earlier here as the multiplication of -pi/2 multiplied by 2 squared. Right? Because it's going to be negative because we were underneath the x-axis during that time. So by canceling that out, we get 7 minus a factor of pi waiting for us there. Okay, so with that, we get these two to compare with. All right. And with that, we need to see which one is going to be the smallest of the bunch here. All right. So with the entirety of, we have 3, 10 minus 2 pi, and then 7 minus a pi. Right. Unfortunately, there is no calculator that's going to be allowed on this section here, but Nonetheless, though, right, we can find the absolute minimum, right? Wait, hang on. Sorry, it's not going to be pi. What am I doing here? This is going to be just yeah. By canceling out, it's 2 pi. I did the canceling out wrong, right? Because it's kind of messy. But the negative pi over 2 multiplied by a 2 squared, right? So by canceling out one factor of 2 right there, this is going to be the 7 minus 2 pi. And that makes life a lot easier. That's how we know for a fact that 7 minus 2 pi, again, we don't need a calculator given that pi is going to be close to the value, even though it's 3.1415 and all the way down infinitely. That by rounding to a simple 3 just for the sake of seeing which one's going to be the smallest, 7 minus 2 pi is going to be approximately 1. 7 minus 2 pi will be approximately 6. Well, 7 minus 6 giving us 4, right? So because of that, right, x being equal to positive 2 is going to be the absolute minimum on this. Okay, and with that, right, our work does show that we've done the consideration of all these parts, the endpoints and the local minimums, as we've been showing mathematically what that looks like, and that will be the entirety of part C here. Okay, and so we can go onwards to part D here, which I think we should actually be able to still fit this in here. So with part D, it'll tell us that for each of f double prime of negative 5 and f double prime 3, okay, right, find the value or explain why it doesn't exist. Okay, very good. So with this, we can go and see we were taking the second derivative, means that we need to go and take the first derivative, which you have the graph of, and take another derivative in respect to x for that again. Okay, so with that, at f of negative 5 being this point back there, right, at the negative 5 on the x, right, we then show that it is part of that line, and so we just need a slope for that, right, going all the across. So we have the 2 points, right, negative 6 comma positive 2, and the other point at negative 2 comma 0, right? So because we're going across 4 and going down by a factor of 2, right, again doing some simple slope of this line here, this means we have a slope at f double prime of negative 5 having a slope of negative 1/2, right, going across 4, going down 2, right, with the rise over run there of a simple slope of a straight line. That's going to be the first part. And f double prime of 3, right, so at f of 3 we're going to be exactly at the corner there between two separate lines, right, one going up and one going down, right? So unfortunately, because we're taking the derivative at a corner, that will not exist, right? So we can say f prime of double prime of 3 does not exist, right, because f prime of 3 is on a corner, right? That mathematical corner is going to be that point in which we have two separate slopes. As you can see, right, approaching at 3, we have a positive slope and then a negative slope after the fact. So we cannot take a derivative on that corner right there because we simply cannot state which one's going to be, right? It will have both a positive and a negative slope at that point. Does not make any mathematical sense to reduce that to a single value right there, because we cannot determine whether we're approaching on the left or the right side of that point. So therefore, because it's a corner, that is enough reason for us to show you that the second derivative of f of 3 does not exist. All right, very good. So we managed to get that all in there through one page. So let's go over to question number 4, and we will be able to go from there. After finishing question number 4, go through some grading of that one as well. Okay, so it tells us here that at the time is equal to 0, a boiled potato is taken from a pot and left to cool in a kitchen. Okay. The internal temperature of the potato is 91 degrees Celsius at the time is equal to 0. And the internal temperature is greater than 27 degrees Celsius for all the time that it's greater than 0. Okay. So the let's see, the differential equation modeled by dH over dt being equal to negative 1 over 4 all of h minus 27, right? This can be used to show, let's see, it includes h of t internal temperature of the potato in degrees Celsius. Okay. So because of this, right, we have enough, like they just give us the actual differential equation. They do not give us the actual h of t function just yet. But nonetheless, though, that is enough for us to get started on part A here, which they're going to tell us to write an equation for the line tangent to the graph of h at t is equal to 0. Okay, and then tell us to use this equation to approximate the internal temperature of the potato at the t is equal to 3. Okay, good. So we can start putting this together here. With that, let's see here. Yep, so because we're doing a line tangent equation and we will need to do an approximation, right? Line tangent means that we set up the equation y equals mx minus h plus k on the outside, right? Where of course h comma k is going to be the point given, which they have already done before here at the h of 0 being equal to 91. Again, at the t equals 0 point, right, being 91 degrees Celsius, right, that's going to be the result of h. So because of that, we have 0 comma 91 waiting for us as the point in which we take that tangent line. Then because of that, m is then going to be the evaluation of the change in the temperature in respect to time at the point at the 0 comma 91 for us, right? So with that, we do our plug-in here of negative 1 over 4 of 91 on the h minus 27 right there. Okay, so because of that, we can set up this line of work here. So 91 and 27, that's going to be 64, right? So 64 giving us negative 16 as a result, right? So we can plug everything here at negative 16 as a slope, x minus 0 plus 91 waiting there. And we get negative 16x plus 91 as a result of that tangent line. Okay, then with that, we're going to approximate at the time is equal to 3. So we can set this as the capital H of 3, so the temperature at the time of 3 is going to be negative 16 times 3 plus 91. That's going to be negative 48 plus 91, giving H of 3 the equivalence to, see, 4891, that's going to be what, 43? Positive 43 degrees Celsius. And with that, we've set up for all of part A. Okay. Then going on to part B, it tells us that we want to use d squared h over dt squared, so the second derivative of h respect to time, to determine whether your answer in part A is an underestimate or overestimate of the temperature at the t is equal to 3 mark. Okay. All right, so with that, we need to go and take the second derivative, right, in respect to time, meaning that we have to go take this and take another derivative of it, right, the dh over dt equation, meaning that we go backwards to the negative 1 over 4 multiplied by the h minus 27 and take another derivative with respect to time. Again, this is a coefficient there, so all we really need to do here is leave it at the negative 1 over 4 dh over dt, right? Derivative of the guy then on the right side is just going to be dh over dt left over on that side, okay? Meaning that we have the second derivative is a d squared h over dt squared is then going to be a negative 1/4, then plugging back dh over dt one more time gives a negative another 1/4 h minus 27. Okay, we can then simplify that as positive 1 over 16 h minus 27 waiting for us right there. Okay, so with that, right, with this being the second derivative of the h over dh over dt, we can then use that to determine if overestimate or underestimate, right, at the time is equal to 3. Okay, so something to note, of course, is that at the time is equal to 3, right, it's going to be 1 over, or the time, that's the only point we know, right? So time is equal to 0, that's 1 over 16, h being 91 minus 27, right? The second derivative. Okay, and because of that, this is going to be what? This is still 64 over 16. It's going to be positive 4, right? This is going to be concave up because it is a positive on the second derivative. And something to know, of course, is that if we have a slope here, and again, we're still decreasing, so concave up and decreasing is going to mean that we're going to take this kind of a route, right, on that equation. Then by taking the tangent line, right, so this is the tangent line, we can take a note here is that because this is going to be, this is a concave, that's concave down and decreasing. What am I doing? Okay, let's try that again. That is not the case. That's concave down. Let's try one more time. Let's iterate this drawing another time here, right? If we're going to show it by a graph here, is that if we're concave up and decreasing, we're going to go along the lines of something like this. Okay, but nonetheless, though, we have ourselves the tangent line coming across here, touching at exactly one point right there, right? So with that being the tangent line, as we see at negative 16, what we started before, and as a slope of that tangent line at negative 16, of course, what that means is that there's going to be, if we extrapolate that outwards to maybe something like 3, there's going to be a clear difference, right? As we can see, it's going to be an underestimate. We're going to be underneath the actual values, right? So because it's concave up and decreasing, it's going to be an underestimate of the value of h of 3. Okay. All right, so we found the second derivative and we come to our conclusion because we have taken the second derivative, understanding is concave up and decreasing as shown in our little sketch there. That's what's going to be the result of that type of estimation. Okay, so it looks like part C is going to be quite long, so let's go and flip the page over to have a look how we can finish off problem number 4. So it tells us here, part C here, that for the time being less than 10, and alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation d of g over t being equal to negative g minus 27 all raised to the 2/3 power, where g of t is in degrees Celsius, okay, and g of 0 is also equal to 91. Okay, so then it wants to find g of t, right? Then based off that, find the g of 3 instead, okay, after the fact. All right, so because once more they give us another differential equation and they give us the initial point and we need to find the original function, it looks like we're going to have to go back to our good old friends of separation of variables to run an integration. Okay. What that means, of course, is that we start with dg over dt being equal to this original function, g minus 27 to the 2/3 power. Okay, and because of that, we need to start separating everything out so that all the g's go to one side and the t's go to another. Okay, so with that, we get dg over g minus 27 all to the 2/3 power is equal to -1 times dt. So we're going to separate the dt's all to the other side so that we can start running an integration. A little bit of cleanup here that I would recommend is that, of course, we instead take this to g minus 27 raised to the -2/3 power as a result of being in the denominator from before, times dg equal to -1 times dt. Then from there, we can run the integration on both sides. Okay, so because this is an indefinite integral, something to note, of course, is how we're going to keep track of the plus c coming out of here, because it is indeed an indefinite integral without limits on the integration. Nonetheless, though, by running an integration of this is going to be g of -27, now this time raised to the positive 1/3 power, keeping in fact of the exponent rule of plus 1 to that exponent spot right there, okay, giving us positive 1/3 and a 3 left there to counter with that 1/3 coming down, equal to a -t plus c, right? And again, that plus c very important for us because we're doing an indefinite integral of this type of problem. Okay. Then moving forth, we need to solve for c. With that, we have the original point, the g of 0, so we have the 0, 91 waiting for us, right? So because of this, we can then plug that in. So it's 91 minus 27 to the 1/3 power is equal to 0 plus c, meaning that c is going to be equal to this result. There's 3 times 64 raised to the 1/3 power. With 64 to the 1/3 power, that's just going to be a positive 4. So 3 times 4 giving us 12. Okay, again, this is going to be equal to c on that part, meaning we can continue down with our line of work here, that we have 3 multiplied by g minus 27 to the 1/3 power equal to -t plus 12. Okay, so with that, we can then divide everything by 3 to start moving things over. So g minus 27 to the 1/3 power is equal to -t over 3 plus 4, if you want to separate that out. Then we raise everything to the 3rd power here to cancel out with that 1/3, right? So that gives us g minus 27 now of all of negative t over 3 plus 4 raised to the positive 3 power. And lastly, g of t, the function on its own, will be negative t over 3 plus 4 to the third power plus 27. A lot of steps here, but plenty enough for us to be able to then revert back to the original g of t equation after taking the indefinite integral on both sides from the separation of variables that they wanted to us to do in the beginning. Okay, but that's not all, of course, because they're still asking to find g of 3 as a result of all that work. So from here, let's go plug that in. So g of 3 is going to be equal to the negative 3 over 3 plus 4 to the third power plus 27. Okay. Negative 3 over 3 is going to be just negative 1, so positive 3 over 3 plus 27, giving us 27 plus 27, giving us 54 as a result of g of 3, and that's of course going to be in degrees Celsius of the potato at 3 minutes. Okay, so as we've shown beforehand, right, if our curiosity does take the better of this moment here, is that indeed, right, with it being 43 degrees Celsius, right, this is going to be, at least in this case, going to be going over, it was me underestimate because the actual was 54 versus the 43 on the actual, right? So us calling underestimate seems to be pretty okay idea for us for that fact of the matter. Okay, so why don't we go back to problem number 3 here, because we can begin to start correcting our work from what we've been doing before. Actually, I wonder if when we move back to reviewing, if I can make sure that we are zoomed in a little bit more, just to, I think something like this. What if we did something like this? We can zoom up a little bit more into our line of work. A little bit cut off right there. Make sure we have a little bit of editing on the fly here, but I think this should be good. Okay. Or better yet, you know what? Why don't we just move my face over on the other side instead? So that way we can see a lot more of the notebook being compared to our actual recording here. Okay. All right. So with that, we have problem number 3. If you scroll down, we're on question number 3 now, right? Question number 3 for this part right here. Okay. Then going on with part A, again, they want us to know that f of negative 6 being equal to positive 3 and f of positive 5 being 10 minus 2 pi. All that is done properly as such with the running of the definite integrals and fundamental theorem, right, of f of negative 2 then being added to that definite integral that we had before there, right? So that all matches up. F of negative 3 being positive, f of negative 6 being positive 3 right there is going to be correct. And of course, keeping in track of f of negative 2 being needed from the start of the problem is going to give us full marks right there, with f of positive 5 being 10 minus 2 pi. With that, part A is going to be 3 out of 3 correct for us. Okay. Then going on to part B here, they ask us on the intervals in which is increasing, which of course going from negative 6 to negative 2 and then 2 all the way to positive 5. Okay. Right, those will all indeed be the exact reasons why that's going to be the case. Okay, so on that, right, everything there matches up with the answers and our justification, so that's going to be 2 out of 2 correct for us as well. All right, then for part C, they want to see where those critical points are going to be, or at least, sorry, they want to find that the absolute minimum, right, the absolute minimum that part C was asking for, right? So because of that, right, we needed to do the comparisons of all the possible candidates. They threw in here, let's see, the negative 2, but that simply doesn't really work out because negative 2 was already going to be an absolute maximum. So there's no point in doing that. Again, they just throw that in the answer key, but of course, the actual absolute minimum value is going to be on positive 2. Right, so let's make sure we clean that. So on positive 2, right, that's going to be absolute minimum value of 7 minus 2 pi. Again, all of our work shows we just have to carry over the 3 and the 10 minus 2 pi from the previous part A on the endpoints, right? So with our considerations of x of positive 2 because of our work on the critical points, and then our answer with this being an absolute minimum is indeed going to give us full points of 2 out of 2 on part C. Okay. Of course, finding 2 out of 2 just meant that we have to use fundamental theorem again, right, with the area underneath the graph of f prime of x. So with that, that all lines up. And then lastly, with part D here, okay, they ran this explanation quite a lot harder than it should have been, right? Nonetheless, though, f del prime negative 5 being the negative 1/2 was exactly what they wanted to see, so that's going to be correct on the first part. But f del prime of 3, right? They did just a full mathematical reason why with the limits and all that stuff, right? All that really does matter for us is because, I mean, it is shown already because it's a corner, right? We have the two different slopes which do not add up, right, to the same one. I mean, again, there are two different slopes on this part of the graph. Okay, so again, just something to note here, right? If you wanted to see it in person, right? Again, at f of 3 for this function, right? Again, that's going to be both an increasing and a decreasing slope at that exact same point. So that would have already been enough to show that it would not exist for the second derivative of 3. So with that, that's 2 out of 2 correct for part D. And so with that, we can line everything up here. That question number 3 is 9 out of 9 correct. We got everything lined up quite nicely with that. So let's go on to question number 4 to see how we've done on that one. All right, question number 4 is going to be the one about that potato. And to begin with part A, right, we're going to do that tangent line, which they wrote out nicely out here with the negative 1/4. Let's see, yeah. Let me double check here. So the negative, oh, that's right, yeah. So first, yeah, the h prime is 0. Sorry, I got kind of mixed up with what was going on here. So the derivative at 0, right, which we've shown right here, right, to find the slope of the tangent line as dh over dt, getting negative 16 as they had right there, right? The slope is going to give us 1 point right there. Then the actual tangent line equation of 91 minus 16t. Again, this is a little bit in a different order, but the actual tangent line does match up exactly the way that they wanted to. And then lastly, they get the internal temperature of that result, giving us 43 degrees Celsius as the approximation as we plug in for 3 in that tangent line. Okay, so with that, this will give us a full 3 out of 3 correct for part A. Then going to part B, right, it's going to indeed, because it is going to be concave up because of that second derivative being equal to the positive 1/16 h minus 27, right? That's exactly shown properly right there, right, for this part of the problem, right? So because of that, it's going to be indeed concave up, and because of that, it will indeed be an underestimate, right, because of its concavity for this part of the tangent line equation. Okay, so all of those do check out. That's still just going to give us all 1 out of 1 correct for us showing the work as to how we prove that it is indeed concave up, leading us to an underestimate from that tangent line equation. All right, let's get to the big one here at part C then, on this other side here, because of course we need to run the separation of variables, right, as shown right there, with the g minus 27 all to 2/3 power being thrown in the denominator there, right, and then the negative dt waiting on the other side with that separation of variables. That's what they wanted to see to show that work to go like that. Then we run the actual integrals on both sides of the equation, and we end up with the 3g minus 27 to the 1/3 and negative t plus c, right? That line of work is exactly correct from running the actual integral on both sides of the equation. Then by setting everything up there, we can get c being equal to positive 12 there, right, as for solving of the initial condition. So that lines up right there. Okay. And then by moving everything over to one side, we do end up with g of t being equal to 27 plus all of the, we'll leave it as 12 minus t over 3, right? The 12 minus t over 3, again, that was just simplified to the negative t over 3 plus 4 on our side. But nonetheless, though, that all lines up with the 27 plus the negative t over 3 plus 4 to the 3rd power on that side. Okay, so because of that, right, we then will solve for g of 3, giving us a positive 54 degrees Celsius. All right, So all of those do line up exactly the way that they should, of course, with stressors here that, of course, if you do not have the constant of integration, if you do not have that plus c in there, you would only get 2 out of 5 maximum if that were the case, right? If that was not there to begin with. And of course, no points at all if there is no separation of variables of this part, okay? So because of that, right, we've gotten everything we needed here, so that's been 5 out of 5 correct for us. Quite nice to make sure that we've gotten everything we needed to with the integration as well as plugging in after the fact. So with that, we have ourselves here with question number 4, 9 out of 9 correct on that part. Okay, very good. So let's go over to our last 2 problems here, and now we'll see how well we've done over the entire packet itself. Okay. So let's swap on back over to our notebook here as we go to the last 2 problems. Again, hopefully everyone is following along quite nicely, or again, any other questions can be sent directly to our email down in the bottom left at labcomath@gmail.com. So with this, let's go over to question number 5 here. Okay, it tells us that 2 particles move along the x-axis Then for the interval from 0 going to t to 8, let's see here. It tells us that the position of particle P at time t is given by the x of p of t being equal to the natural log of t squared minus 2t plus 10, while the velocity of particle q at time t is given by, now the velocity equation, v of q of t being equal to t squared minus 8t plus 15. Okay. And they also tell us that the particle q has a position, so xq of 0, is equal to 5. Okay. Alright, so we got all of that listed out for us right here. So with this, again, we have part A right here, that for the interval 0 to t to 8, when is particle P moving to the left. Okay, so with that, right, if we're moving to the left, that of course is going to mean that the velocity of P, right, must be less than 0. Okay, again, not to be confused with velocity of Q, right? This is going to be, instead, by finding the velocity of P, means that we have to go and take the derivative of the position of P in respect to time, right? That derivative respect to time, then we can make that conclusion to take a look to see if it's going to be less than 0 on that. Okay, so by then taking the derivative of the position, right, that means we take the natural log t squared minus 2t plus 10, and we're going to take that derivative in respect to time from there. All right, so with that, that means we just follow along with the natural log rule, 1 over t squared minus 2t plus 10. Then with chain rule, coming after the fact of taking the derivative of the natural log, it's going to be 2t minus 2 on that side. Then means that we just simplify, put everything together, negative 2t minus 2 all divided by t squared minus 2t plus 10. Okay, very good. So with that, we can go ahead and put this through here, right, that we want this to be less than 0 in order to be moving to the left as was described. Okay, if that's going to be the case, all right, we need to go and see where in this time frame where, let's see. Very interesting how they're doing that, because we need to find the right zeros on this. Huh. Yeah, because with the t-squared minus 2t plus 10, that's going to be a little bit odd with the actual results of this equation. Okay. Well, in any case, though, we have at least... No, actually, no, it shouldn't really matter because we're never going to be negative in any case on this, right? Yeah. So, because we have the numerator of 2t minus 2, right? Again, because the fraction, we can see where either of these, right? Or the t squared minus 2t plus 10 is in 0. At least for in this case, right? If we're starting at 0, right? So at 0, and the denominator, right? It's 0, 10 for the first order pair right there. And then because we go all the way to positive 8, right? It will never really reach anything higher than negative because, right? At 8, it will give us a much more higher number. What, 64 minus 16 gives what, 48? So 58, right? So the denominator will never really go to negatives in the first place because of this, right? And because of that, we then can only look at the 2t minus 2 on moving left, which it will, right? When the t is going from, right, if you want to make the note here, so 2t minus 2 is less than 0 when the t is going to be, right, between 0, because that's where it can start, and then all the way up to 1, right? Because that 1, it will be equal to 0, and anything beyond that will be greater than 0 because of that, okay? Right? So we can finally make note here that the particle P moves left from the interval from 0 to positive 1 on t. Okay. Very good. So that lines up pretty nicely. Then for part B here, says that for the 0 going from t to 8, find all the times t during which the two particles travel in the same direction. Okay. So if we're going to go same direction, right? Because we know that the particle t only goes the left from 0 to 1, right? What that means is that we can already make our number line decision on particle p here, right? So going from 0 to 1, that's going to be on the negative direction. And then all the way to 8, it's going to be in the positive direction. All right? So with that, then we need to find the directions for particle q, right? And we'll pull up another number line for that, which means we need to look at the VQ of t, right? If it's like less than 0 or greater than 0 along that time frame, right? So because V of q is going to be t squared minus 8t plus 15, what we can do, of course, is that we can simplify this into a simple quadratic, so it's negative 3 and t minus 5 as a result, right? So because if you want to find where it would be less than 0 on that time frame, that means that positive 3 and positive 5, those are going to be, at least in some aspect to this number line here, that's going to be where we'll be checking this out. So let's say at the t is equal to 0, it's going to be positive, right? Because they're both being in the negatives on both factors of that. So all that will be positive. Then in between a t is equal to 4, that's going to be a positive multiplied by negative. So that's going to be negative on the velocity, right? And then lastly, when t is greater than 5, so maybe t is equal to 6, that will be positive on both sides of each of the factors, making it a positive as a result on that velocity as well. Okay. Which means is that between 3 and 5 and 0 and 1, because those will never match up with them both moving to the left, we can only really look at the parts in which they're both moving to the right. So with that, right, the particles P and Q move in the same direction. Between the two different, so now we have between 1 to 3, because 3 is where the Q then switches direction afterwards to the negative side. So going from 1 to 3, okay, and then onwards, right, from 5 to 8, right, because 5 is where Q switches back to the positive direction, particle P stays in the positive direction during the entirety of that time. So from 5 to T to 8. And those would be the time frames in which those particles will be moving in the same direction. Okay, very good. Then for part C here, it tells us to find the acceleration of particle Q at the time is equal to 2. Okay. Is the speed of the particle Q increasing, decreasing, or neither at the time is equal to 2. Okay. And we need to show why. Okay. So acceleration of particle Q, of course, meaning that we're going to need to go and take the velocity of Q respect to time and take that derivative once more to take the acceleration of Q at any given time. Okay, so then by taking that derivative, that means we need to go and do the velocity of Q, which was t squared minus 8t plus 15, right? All this, take that derivative, and with that we get the acceleration equation instead of 2 times t minus 8, right? Okay, making it the acceleration. Okay, then you see that, right, is the speed increasing, decreasing, or neither at that time. Okay, so at the time is equal to 2, so we can then go acceleration at the time is equal to 2 is going to be 2 times 2 minus 8, giving us negative 4. Okay, and so because it's going to be the speed, right? So first off, let's first write that out. Right? So acceleration of 2, that's what they wanted to find, right? But then if they're looking at speed, right? Speed is going to be the comparison. And speed compares A of 2 and V of 2, right? To look at the signs of them. Same sign being increasing speed, and then different signs meaning decrease of speed. So in the same fashion here, right? So we have to look at V of 2. So by putting that together, right, we just plug that right into the original velocity equation of 2 squared minus 8 times 2 plus 15, giving us 4 minus 16 plus 15, giving us positive 3. As a result of all that, again, this is going to be velocity. Okay, so because, right, the velocity is greater than 0 and the acceleration is less than 0, so different signs on the acceleration and velocity, right? Particle Q is, let's see, has its speed decreasing at the t is equal to 2. All right, very good. Yeah. So because this, right, that difference in the signs, that's what we need to look at, right? The difference in signs for the actual velocity and acceleration, right? That will then determine what the speed will look like for that particle. Okay, let's see. Let's look at part D here. So it tells us to find the position of particle Q the first time it changes directions. It changes directions. Okay, so because it's going to be changing direction, right, at a specific time, right, we've already kind of settled that already in the velocity, right? This is the velocity of q. And back in part B, right, again, we want to looking at direction wise, right? And if it's going to change direction, this is going to be at the time is equal to 3, because q velocity was changing from positive to negative direction, meaning that at time is equal to 3, right? That's going to be that time that's going to happen. Okay, and because of this, right, and because we're only given, right, we're only given the velocity of q at any given time, but we do have a position of q at the first time of 0, right? So because of that, looks like we're gonna have to go and use good old fundamental theorem of calculus once more here, where if we then took the integral of the velocity of q going from 0 to 3, right, so velocity of q in respect to time, that means that it's going to reduce back down to the position at 3 of q and the position of q at the time of 0. Okay, so with this, if you want to find the velocity at 3, or it's not the velocity, the position at 3 for the particle q, that must mean that it's going to be, instead by moving that xq of 0 over to the left side, that's xq of 0 added with the definite integral 0 to 3 vq of t dt. Okay, meaning that we have to go and put in that, let's see, that positive 5, right, that was at the start of the problem, then added with the definite integral, right? At least in this case, we can run the definite integral of the velocity equation that we copied down up there. So that's going to be 1/3, let's see, t to the third power minus 4t to the squared plus 15t. And all this will then be evaluated from 0 to 3. Okay. Unfortunately, it looks like we're going to have to flip this over because we are out of space already, unfortunately. So we just need to go and move this back here. So still, it's going to be the position of q in respect to time. Sorry, at the time of 3, which is going to be 7. Why am I say 7? It's 5. Plus then the 1/3 t to the third minus 4t squared plus 15t, evaluated from 0 to 3. Okay. So with that, we just do the definite integral evaluation, and then we should finish this problem up here. So this is going to be, well, the 1/3 3 to the third power minus 4 3 squared plus 15 times 3, right? And with that, we just subtract zeros from the bottom limit with t's all in there. Okay. And so we can put everything back here. So 1/3, right, we can take off a factor of 3 right there. So it's going to be 9 minus the 9 times 4 makes it 36. And 15 times 3 gives it a 45. Okay. So 36 and 45 will give us back a positive 9. So this is going to be 5 plus an 18, giving us 23 as a result. Okay. Again, this is going to be the position of q at the time of 3. At least for the sake of space here, we can go and put this all back here. So I'm going to write down, making sure that this can be seen here, is that I'll just copy it down here. Our work was still going to be the same. We just did the actual result of that definite integral. So the position of q at 3 was going to be 18. No, it's not 18. It was going to be 23. 18 was the result from the definite integral. 23 was the result that we wanted to see right there. Okay. There's a few misclicks right there on our side, but nonetheless, though, that should have finished it for problem number 5. So let's go lastly to problem number 6, and we can finish this off for this packet here. All right, we have a table here, which we get the values of x. Then going down, it's going to be g of x, and then going down is going to be g prime of x. Okay, so we go -5 on that, and then -4, -3, -2, -1, and 0. Okay, then it's going to be 10, 5, 2, 3, 1, 0. So 10, 5, 2, 3, 1, 0. Okay. On g of x, and g prime is going to be -3, -1, 4, 1, 2, 4, 1, negative 2, and negative 3. Yeah, making sure we copy that down all properly here. Okay, and then we can go and put this through C. We go across 6, it looks, no, 1, 2, 3, 4, 5. Yeah, go across 5 and 5 on either side here. Yeah. Okay. So 1, 2, 3, 4, 5. And we have our whole axis right here. 1, 2, 3, 4, and 5. Okay. Then we go up 2 and down 2. Okay. So we have the graph of H here. Okay. And let's go and copy this down. So at the negative 5 comma positive 1, you go there. And then at negative 3 comma positive 2, negative 1 comma positive 1, and 0 down there. Then we go all the way to positive, looks like 3 comma negative 1. And then it's going to be 4 comma 1, and then 5 comma positive 3. Yeah, that just makes sense. That makes sense right there. Okay, so let's go ahead and connect this going across there. So we go all the way down to 0. And then we go across there. And then we go straight up right there. Okay. There we go. That puts that nicely for the graph of H right there. So I can go in from negative 5 all the way to positive 5 right there. Okay. So for context, it tells us that we want to let f be the function defined by f of x being equal to cosine times 2x plus e raised to the sine x power. Very nice. Okay. Then they're also going to say that let g be a differentiable function let's see, then it says that the table above will give all that. Okay, very nice. And the table does show those values of g that they already have right there. So yeah, we have graph of H already right there. So then for part A, they're going to ask us to find the slope of the line tangent to the graph of f at x is equal to pi. Okay. So because we're getting a line tangent, right, at x is equal to pi, that must mean, right, that we're going to need to find f prime of pi to give us that slope. And of course, the equation must be equal to mx minus h plus k, all like that, right? And that's the tangent line equation, right? And then h comma k, of course, going to be the pi in the h, and then k going to be f of pi. Okay. So because of this, let's go and find each one of these individually here. I got a lot of work cut out for us here. So f of pi from the original equation right there at the cosine 2x plus e raised to the sine of x. We just plug everything there. So the cosine of 2 times pi plus e raised to the sine of pi. Okay. With this cosine of 2 pi, thanks to our lovely memory from the unit circle, this will all go to 0. And sine of pi will then go to 1. So this is just going to be 0 plus e to the first power, giving us a nice e. Wait, hang on. No, sine of pi is actually equal to 0. Cosine of 2 pi is equal to 1. My memory is not serving me the way that it should. Alright, so the 1 plus e raised to the 0 power, which is going to be a positive 2. Alright, good thing we caught that. But nonetheless though, f of pi will then give us the result of pi comma positive 2 as for the point right there. Okay. And then lastly, f prime is then going to be instead, right? So f prime of x for us from our original equation, to work that out, is going to give us negative 2 times the sine of 2x, keeping track of chain rule along with the cosine rule, going back to negative sine, and then plus e raised to the sine x. So again, chain rule is going to dictate that's going to be cosine of x multiplied by e raised to the sine of x all that left exactly the way that it is right there. Okay, so with that, we need to plug back in f of pi once more, okay, giving us negative 2 sine of 2 pi plus the cosine of pi times e raised to the sine of pi right there. Okay, so with that, sine of 2 pi, now this is going to go to 0 again. Sine of pi is going to go to 0. Cosine of pi is going to be negative 1 right there. So this is going to get us all of 0 plus the entirety of negative 1 times e to the 0 power, which is going to be positive 1, which will give us negative 1. Again, this is the f prime of pi that we solved for after taking the derivative, giving us the m slope for us, which in its finality here will give us the slope equation of y is equal to negative 1. Again, given that's a slope of x minus h, so it's x minus pi, and then k will give us positive 2, waiting for there as a result. Okay, I don't know if the graders are going to simplify that, so if you were to give this an extra step here, that's going to be negative x plus pi plus 2, which will be what here, this will be I guess pi plus 2 minus x if they wanted to do it in that case. Again, it doesn't really matter. What we have in the box is just going to be good enough for them, showing how we can get that equation. Alright, part B tells us that let k be the function defined by k of x being equal to h of f of x. Okay. Then they wants to find k prime of pi. Okay, so with that, we then need to find k prime of x. Again, this is going to be chain rule coming in hot over here because we have a function inside of a function listed out right there, which in this case is going to be h prime of f of x, then multiplied by f prime of x. Okay, that's going to be a result of chain rule. So with that, we can then plug in for pi. So k prime of pi being equal to h prime of f of pi, and then multiply by f prime of pi. Okay, so thankfully, we've already found f prime of pi, as our work in part A already implied, right? F prime of pi back there, right? In this part, giving us negative 1, right? So first off, h prime, now f of pi though, right? We still need we found earlier as well, right? F of pi, which we found also in part A, was going to be positive 2 after our work right there, right? So multiply by negative 1. Then h prime of 2, right? So as you can see at the point of 2 back there, right? We're on the graph of h. Oh, sorry. At the point of 2 right there, again on the graph of h, we need to find that derivative coming down on that slope right there. Okay. So because we have the points at positive 3, comma, negative 1, and that's what that point's supposed to be, at 3, and then at 0, comma 0, right? We realize that we are coming across 3 and going down by 1, right? Giving us a slope in this case, right, with rise over run, giving us negative 1, 3, right, as that slope. So in this case, this is going to be negative 1/3 multiplied by a negative 1, giving us a positive 1/3 as a result of that. Okay, so that's going to be k prime of pi waiting for us right there. Okay, then going on to part C, it tells us that to let m be the function m of x being equal to g of negative 2x times h of x, and again we want to find from here m prime of positive 2. Okay, so now we've got a lot of things going. Now we got product rule to keep track of, right, and chain rule, right, because m prime of x because we need to find that first derivative response of this function here is going to be, right, so this g prime of negative 2x multiplied by a factor of negative 2 as a result of the chain rule, and then multiplied by h of x, then adding that with g of negative 2x times h prime of x. Okay, so then by finding m prime of positive 2, this is going to be g prime of negative 4, and then times h of positive 2. We can leave that negative 2 coefficient after we solve the rest of that, plus g of negative 4 times h prime of 2. Okay, now, thankfully, we've already found h prime of 2. Again, we've really found that earlier on the previous part right there. So this is going to be negative 1/3 right there. Okay, then h of 2 we found earlier as well at, well, almost, because 2 at 2 right there, right, that's going to be in between, right, in thirds coming down to negative 1. So at 2 we're going to be the negative 2/3, and the negative 2 coefficient stays, and g prime and negative 4 can be easily found on this table here that they gave us. Right, g prime at negative 4 on the x is going to be a negative 1, keeping in each of those lines there. Okay, so it's negative 1 there, and on the same table, g of negative 4 was going to be a positive 5 on the original function. All right, so we have everything listed out right here for everything that we need to solve for. So by going through this line here, negative 1, negative 2/3, and a negative 2 will give us a negative 4/3. And then 5 and negative 1/3 will be a negative 5/3, giving us total of negative 9/3, giving us entirety of negative 3, giving us m prime of 2 finally. Okay, a few lines of work, but everything should be fairly straightforward with how to find these derivatives and going through the graphs and tables. So with that, there's part D here asking us, is there a number C on that interval negative 5 to negative 3 such that g prime of C is equal to negative 4. Okay, well, if we're looking to confirm a specific C on the first derivative of a graph, what could that mean, right? Okay, the first part, okay, we can go through a couple of things here, right? But I think the first off is that this sounds a lot like mean value theorem for us, right? If you want to know, MVT is the mean value theorem. Of course, meaning that we can then do the average rate of change, right, for that interval from negative 5 to negative 3. So with that, that's going to be g, because we're doing this for the first derivative of g. So this is going to be g of negative 3 be minus g of negative 5 over negative 3 minus negative 5, like that. Okay, so with this, we can go put this together. So g of negative 3 from the table is going to be a positive 2 minus g of negative 5 being a positive 10, all over 3 minus negative 5 is going to be a positive 2. Okay, and keep making sure that it's a minus a negative, making it back to a positive, giving us negative 8 over 2, giving us negative 4, right? So because the average interchange of negative 4 does match what they're asking for, right? Okay, that will conclude that yes, right? According to the mean value theorem, right? A C is guaranteed to exist on that interval from negative 3 to negative 5, we're going left to right, so negative 5 to negative 3, okay, where the g prime of C is equal to 4, negative 4. All right, very good. Put that right in there to fit inside of that page right there, and that will conclude it for part D. A little bit of understanding of mean value theorem and what that entails. But with that, that should just about do it for this exam. All right, good. So let's go back to our corrections here and back to part number 5 here so that we can then compare to see what we have scored so far. Okay, so let's swap over here. Again, go into question number 5. Okay, well, we have those two particles right there. Okay, so for part A, again, they were looking for exactly the time in which it's going to be moving to the left, right? Again, we need it to be, well, they already stated that's going to be greater than 0 for the denominator, right? But we're looking for all the times in which the derivative of the position of p is going to be less than 0, right? And it does show that after running the integral, right, not integral, sorry, the derivative, right? So the entirety of this fraction of the the 2t minus 2 on the numerator and the t squared minus 2t plus 10, right? Again, that derivative does match exactly the way that we were supposed to. And then lastly, we get the correct interval going from 0 to 1 only for that numerator part. So with that, our answer does line up with what they wanted to see. And with that, we get the resulting that we have 2 out of 2 correct for part A, with only the interval from 0 to 1 being correct. Okay. We have a viewer of Yusuf asking if I'm good at chemistry, which first off, yes, I am. I do have a degree in chemical engineering, but then he asked how to make 99% pure methamphetamine. Well, unfortunately, the laws in my country does not permit me to go teach that to people, sadly. So unfortunately, you're gonna have to go elsewhere, as you will not get any of the answers here. There are actually going to be ways, I'm sure, if you do take a look close enough, but that's going to be a very big question of legality in wherever you're going to start doing that. So, nonetheless, though, unfortunately, that wouldn't be answered here, but hopefully, Yusuf, you can find what you're looking for maybe somewhere else instead of here. Because right now, we are still focused on finishing out this exam paper here. Again, we're doing the AP Calculus exam. Again, something more math related, but nonetheless, though, yeah, chemistry questions direct can be answered elsewhere, right? But of course, that's a classic one. People wanted to know if some very questionable substances can be made with chemistry, which of course they can, as many TV shows have shown that, but in reality, that will have to be asked elsewhere. Okay, nonetheless, though, let's move forward here on part B on this question here. So they're asking on part B, again, they want to see where the two particles are traveling in the same direction. Right, meaning that yes, in the same way they did the number line analysis to make sure to see where those velocities would line up, whether they're going to be positive, right, or negative on other times. So everything does line up with particle P. Again, the change of direction happens at the time of 1, which we do show in our number line right there. And then from 3 to 5, right, those 2 times for particle Q as well. So because of that, right, our intervals do line up, right, with the going with the intervals from 1 to 3 and 5 to 8, right? So both of them do line up exactly the way that they should. And the analysis does match up with our number lines as to where we can see where those particles move in the positive direction and those that move in the negative one. Okay? All right. Very good. So with that, that's going to give us 2 out of 2 correct for part B. Okay? Then for part C, it's going to then ask us to find, right, the acceleration of particle Q, right, at a given time. So the acceleration, of course, is going to be the first derivative of the velocity, which we've shown exactly in our line of work right there. Okay. Then by running it through, we do finally get our acceleration at the specific time at -4, which is exactly what they want to see right there. Then from there, because they want to know the speed on top of that, right, we need to go and check what the acceleration and the velocity signs were going to be. And because our velocity was a +3 at that given time, right, we then get to see that, right, with 3 being greater than 0, the speed will then be decreasing because its velocity and acceleration have opposite signs as a result. Okay, so because of that, all those do match up the way that they should. So that's going to be 2 out of 2 correct for part C. Okay. And finishing up here, we have part D. They're asking for the position of particle Q at the time it first changes directions, which, as noted here, at time equal 3, that was indeed going to be the case. So by running fundamental theorem of adding xq of 0 onto the side of the definite integral from 0 to 3 for the velocity equation that we had, we ran the actual definite integral, as you can see on our last space right here, with 5 plus that evaluation of 1/3 t to the third minus 4t squared plus 15t, all shown there in the definite integral analysis. We do end up with a +23 waiting for us as the position of q, and that is indeed going to be correct. So again, they want to see to make sure that we know how to do the definite integral and the initial condition of xq of 0 to make sure we can add that back into the result to get 23. All adds up to us getting 3 out of 3 correct. Okay. All right. Then lastly, let's go over to number 6 over here. Okay. To finish everything off here is that they were looking to see, right? First off, we want to find f prime of pi, right? For that line tangent, okay? Right, just the slope itself. So we do get -1 as a result, right? For our work here, right? -1 as a slope of the line tangent was indeed just going to give us all 2 points, right? To know how to take that derivative of pi, again, at -1. So with that, that's going to be 2 out of 2 correct. Okay. Then going to part B over here, right, they wanted to find the k prime of pi on that side. Okay, so because we had to make sure we understood the chain rule of finding k prime of x, right? That was exactly what they wanted to see. So that will give us 1 point already for just doing the derivative of k of x. Then by plugging in pi after the fact and running everything through, right? Making sure that we keep track of everything, a positive 1/3 was going to be the result of the answer. Okay. So then going to part C here, they said let m be the function m of x that was described as such, and they want to find m prime of 2, right? So because they wanted to make sure that we knew how to do m prime of x properly, all written out there, right? So let's see if we got that correctly. Again, that's going to be g prime of 2x times that -2 coefficient times h of x, all in this first part right there of the particle. That does all line up exactly, just that -2 was moved to the left side, but still the exact same result. And then we get g of -2x times h prime of x, right? So both parts of that is going to be correct on our product rule, giving us 2 points so far on that. And then lastly, by plugging in +2, we get a -3 as a result of m prime of +2, right? So that does match up properly right there. Okay, so that's going to give us a full 3 out of 3 correct on part C. And then lastly, by going through and to prove that g prime of c is equal to -4, right? They wanted to see if there was a number c on that interval from -5 to -3 where that would be true. Again, they did the same exact thing of using mean value theorem, right? As they stated right there. We have to go and take the average rate of change, which by looking at the table and looking at the difference between g of -3 and g of -5, we do get a result of -4, which matches exactly their proposition of that specific derivative point. So because mean value theorem does guarantee that, that would be the case. So again, getting 1 point already for the rate average rate of change, which they wanted to see, and showing with mean value theorem that was going to be the case. That gives us another 2 out of 2 correct. All right, very nice. So we can move back here to show that with everything listed out properly. So question number 5 was 9 out of 9 correct, and question number 6 was going to be the same as well. Okay, right? We got everything up there except for that one mistake on question number 1, where we put something incorrectly in the calculator. But with that, that is all 53 out of 54 correct on the 2014 AP Calculus exam question packet. Okay, so with that, that will just about do it here. Again, this could have definitely been a perfect score again for us if only we actually kept in mind the actual last moments right there, where we had to put the right numbers inside the calculator. But nonetheless, though, I think this is a very successful stream for us again, where we have gone over every question, and which will be recorded again once more on our channel for everyone else to see and follow through. Again, any of the emails can be answered to our email over there on the left side, labcoatmath@gmail.com. And again, we'll be moving on to chemistry soon enough with the next couple weeks here. We'll be finishing up these last few bits of AP Calculus. And lastly, we'll be able to go through these last few moments together. So with that, that will do it for today. And we'll be back again next week, Tuesday, for PM PST for another section of AP Calculus. So with that, again, we thank you all for tuning in today. And we'll be back again on next Tuesday.